Hello, this is a problem-solving video about recursion. So what's going to happen is going to talk something about recursion and talk about recursion in the context of iterative solutions, which is another problem-solving technique that you may be familiar with in computer programming. So an iterative solution to a problem might be we want to calculate the sum of a certain amount of numbers. So this loop would create the sum of 0, 1, 2, and 3. So it would add those numbers together. So you can see it goes through a process. It starts off with sum being 0, then you add 0, then add 1, then add 2, then add 3, then print out the sum. Each step means you add another number. So it's a very clear process. So we call this an iterative approach. You know how much memory it's going to use. You know what's going on as we go through the program. On the other hand, recursion. So here's a visual example of what recursion might be. On the screen, there's a picture of a woman with a cereal box. On the picture, on that cereal box, there's a picture of a woman with a cereal box. And within that cereal box is a picture of a woman with a cereal box. So when would you stop when painting this picture? So just get smaller and smaller. In each one, there's another version of the problem. And this is kind of what recursion is about. So the solution to stopping is there's a base case. And we'll talk about this in detail in a few slides' time. Another example of recursion from real life is how do you tell if someone's is a descendant of Genghis Khan? Well, you're the descendant of Genghis Khan if your father is named Genghis Khan or if their father or mother is an heir to Genghis Khan. So the base case in this case is if your father is Genghis Khan. So you keep going up your family tree until someone's father is Genghis Khan. And only when you've reached the top of that tree, then everyone who's related to Genghis Khan is, circular argument, is related to Genghis Khan. But the point is you only know that when you find Genghis Khan and find out that someone's father is Genghis Khan, and you know when to stop. So when you're following an iterative process, you kind of know what's going to happen. It's that addition to create the sum. You add something, then add the next thing, and you kind of know when you're going to stop. In recursion, you don't necessarily know when you're going to stop, and that results in infinite loops at times. If you don't get the correct base case, you may never stop. And so in a computer's case, generally speaking, it would never ever stop. Now you might find on your particular computer and on programming you use, your operating system will stop you after a certain amount of time doing the same thing over and over. But in theory, it would go on forever. And because of that, you don't know before you've run the program how much memory is going to be used, because it can just keep going until it reaches that case. And even talking this through, we can see that recursion's a little bit harder to understand than, in inverted commas, normal programming with an iterative solution. So here's a problem you might want to solve. You want to count down from number the user gives. So if you gave 5, in this function, if the number's less than 1, you'd stop. If not, you print the number. And then you run the same function with 4. And then you do that first line again. Is 4 less than 1? No, so we don't stop. We'd print 4. Then you run the function again with 3. Is 3 less than 1? No, so we print out 3. Then we run it with 2. Is 2 less than 1? No, so we print out 2. Then we run it again with 1. If a number's less than 1, well, 1's not less than 1, it's equal to it. So we'd print out 1. Then you'd run countdown with 0. And at this point, the number is less than 1, so it stops. So this is a way of printing out the numbers from, in this case, in this example, it was 5 to 1. And here's another explanation of that using 2. So if you feed in 2 to countdown, it will print out that value and then run countdown 1. And then it will use 0, feed it in again, but then it will stop. And that's the base case. That if the num is less than 1, return. That's the base case of the algorithm. So you always need to know when to stop, which is that base case in recursive algorithm. And also, before you run the code, the computer doesn't know when that will stop. It will keep running these, we'd call them instances of the function. So on the screen now, there are 3 instances of the function, 2, 1, and then last one it stops. Factorials are a real example where you're multiplying 2 numbers together. 4 factorial is 4 times 3 times 2 times 1. So 4 factorial is in fact 4 times 3 factorial, and 3 factorial is 3 times 2 factorial, 2 factorial is 2 times 1 factorial, and 1 factorial is 1. So this is a great opportunity to use a recursive solution because each solution is in itself a different case of the same problem. So you could write an iterative solution to that, and here's one on the screen. You would know how many times that would run, num times. So in this case, you know it will run 4, and the computer would know that before it starts. But in the recursive sense, you're just going through. Now, you kind of only know the answer when you've done the final base case, which in this case is 1. So we're seeing in this forward pass, 4 factorial is 4 times 3 factorial, which is 3 times 2 factorial, which is 2 times 1 factorial, which is 1. And once we have that 1, we know that 2 factorial is 2 times 1, we know that 3 factorial is 3 times 2, and we know that 4 factorial is 4 times 6. And then you're able to come up with the solution. Fibonacci sequence is exactly the same thing. We only know the end result when we of the overall end result when we have the final one if we choose to use a recursive algorithm for this. So here you go. The Fibonacci has 2 base cases, or you could combine that to 1. If n is 1, you return 1. If n is 0, you return 0. So Fibonacci 2 would be Fibonacci 1 plus Fibonacci 0, for example. And when you have these recursive techniques, you can actually model them as trees. So here's a way of modeling Fibonacci 4 by saying Fibonacci 4 is made up of Fibonacci 3 and Fibonacci 2, which themselves are made up by that third line in the tree, that third level, which itself, Fibonacci 2 is made up of Fibonacci 2, because those are the base case. So, recursion's a different way of problem solving than in some cases you are familiar with. There are some solutions which are not great recursively. Let's just think. Recursion's a bit tricky to understand. So you might want to create a solution which is iterative because it's easier to understand. And also there might be situations where you want to know how much memory is going to be used beforehand, so you would perhaps shy away from using a recursive solution.